Okay, so I want to start with a couple things. Alex, what were you supposed to remind me about at the very beginning? Was it the flags and printf? Okay, good. That's what I thought. Okay, so I want to just demonstrate something here that can happen. So let me just make a really simple, quick program, and I'll deal with all this stuff later. And let me change this to ARM assembly. Okay, so let's just make a quick program. Data, text, global main, uh, store pair, x29, x30, stack pointer, -16, exclamation, load pair, x29, x30, stack pointer, 16, move w0, immediate 0, and return. He lives. Okay, in the data section, let me go ahead and just define a simple string here, nothing really fancy. Um, okay, the number is %i. That's it. Nothing really particularly special. And all I'm going to do is I'm going to move an immediate to W0, or sorry, W1, because what do I have to put in W0, or X0 rather? The address of that string, right? And then I can print it. Okay, so all this is going to do is print the number 5. Okay, and we've done that plenty of times, so that's not what I want to concentrate on. Okay, so let's assemble it real quick. And where did I put this? Print and flags. So let's, and I'm going to assemble it with the debugging flag. Okay, so all it does, right, is print 5, no big deal, right? Okay, so that's not what I wanted to kind of concentrate on, but rather let's go into here and let's run it through GDB. Okay, so it's about to execute that instruction, and I'll go ahead and step through to that one and step through to that one. Okay, so if I look at the registers, what's in register 1 at this point? 5, the number 5. What's in register 0? At this moment, it happens to be the number 1, but there's nothing special about that. It will get replaced here in just a second with the address of the format string. Okay, but in particular, what I want to look at is what are the flags that are currently set? The carry and the 0 flag, right? Okay. Now, did we do anything so far that would have set the carry or the 0 flag? No. So those just happen to already be set when our program started, okay? And if I step further and I print, okay, it just so happens that the carry and the 0 flag are still set by printf, or are still set after printf. Okay, but you can't necessarily assume that printf is going to keep the flags as they are. Okay, so where this is potentially going to cause an issue is with the poor man's 128-bit arithmetic, depending on how you structure it. Because if, let's say that you print the 4 numbers and then you do the addition and decide whether or not you should print the extra string that a carry occurred or did not occur. Okay, then you won't have to worry about this. But if you print if you do the addition before you print, Okay, what's the addition is going to set some flags, right? Okay, but then if you print, how do you know that the print isn't going to change the flags on you? It could. Did it in this my example here? No, but theoretically it could have. Okay, so what do in order to preserve the flags for later so that they're what they were before you printed? What can you do? Well, what was the pair of instructions that allowed us to kind of get at the flags? So it was MRS and MSR, right? So MRS and MSR allow us to move the flag register to a regular register and vice versa. Okay, so for just sake of demonstration, let me put one of those in here. And let's put it in W2, say, well, is it X2 or W2? Well, we'll just do W2. And then what is the flag or the register called? NCCV, right? So this is going to copy the flag register to W2. All right, so let's reassemble it. And oops. Yeah, I have to do X2, not W2. Even though it's only 32 bits, that's okay, whatever. Okay, so let's go back into GDB for that. And okay, so what happens to be set right now? The carry and the 0 flag. And what's in register X2 at this moment? Blah, 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 big number. Okay, but if I execute this instruction, now what's in register 2? Okay, it looks like it's a big number, right? And that's only because of which bit positions the status flags are in. So the status register, which is down here, CPSR, okay, is a 32-bit register. And the flags part of it, the carry flag, the 0 flag, the negative flag, and the overflow flag, right? Those are just 4 flags. So that's just 4 bits. So all that it's done is it's copied the 4 bits, bit number 28 through 31. Okay, so what's the lowest bit? Bit 0, because we have to start counting with 0, right? Okay, so it's copied the 4 highest bits of the status register, okay, to register X2's 4 highest bits. Okay, so which bits are they? Well, 6, right? What is that? That's a 1 in the 4's place and a 1 in the 2's place. Yes? Okay, so the 4's place is one of the flags, and the 2's place is the other flag, right? And we only have 2 flags set. In this case, the carry and the 0 flag. Okay, is that good? And in fact, what's the order of them? The order is NZCV. And does that make sense given which 2 flags are set here? So what flags are set in our case? C and Z, right? Well, which positions are C and Z in? The 2's place and the 4's place. And that's why it's 6 in the hex. Okay, Patrick, you don't seem convinced. Or 4 and 2 make 6, right? Okay, so 2 and 4 make 6. And which positions are the C and the Z in? In the 2's place and the 4's place, right? Well, last time I checked, 2 plus 4 is 6. And then That's why that's a 6 right there. Okay, because it corresponds to those 2 bits being set and the other 2 bits being 0. Okay, so what would that, where I've got the highlight, what would that read if all 4 bits were set? F. What would it read if none of the bits were set? 0. And then every combination is possible, right? Okay, so um, this means, and this actually is the second point I wanted to make here, is before we even did anything here, before we did, like, so I don't have any addition, hang on one sec, in here. The carry and the 0 flag are already set. We didn't set them, right? Something else set them before we got to our program. Yeah. They're not set. So they would show up here on the line CPSR if they were set. Okay, so where are the N and the V? Well, right now they're zeros. Okay, and so, but this is the order that they would be for those 4 bits. Yeah.
So it's 6 because the N is a 0, you have a C and a Z, and then the V is a 0.
Exactly, right? Because, so they're in four bits, right? And I want to think of this as the 1s, 2s, 4s, and 8s place. Okay, well, the N and the V are not set, so those are zeros. And the Z and the C are set, so those are 1s. And, well, 4 plus 2 is 6.
So if they were all set, it would be F.
It would, yes, exactly. If all 4 flags had been set, we would have an F right there. If none of them are set, we'd have a 0, and then any combination within that also could happen. Okay, does that make sense? Okay, so the other thing I wanted to point out is the carry flag just so happens to already be set before we're doing anything. Okay, yes? So what would happen if I did the command add CS to add 1 and 1? What would I get as my answer? The number 1 plus the number 1 with add CS. I would get 3, not 2. Why would I get 3? So what does add CS do? If I add 2 numbers, let's say 1 and 1, what should I get? 2. Okay. Add CS also adds in the carry flag. If the carry flag is set, it adds that extra 1. If the carry flag is not set, then it doesn't. Okay, so if we added 1 and 1, we would get 3 because the carry flag is set if we use add CS for our addition. Okay, do we want that? Well, maybe. Can I say maybe because in the 128-bit addition thing, you're really doing 2 additions, right? You're doing the low addition and then you're doing the high addition. So what command do you want for the low addition? Add S. What do you want for the high addition? Add CS. Okay. Why do you want the carry for the high but not the low? Because you might have to carry from the low addition to the high addition. But should you carry anything into the low addition? No, because it's the first addition. Okay. So does that make sense, the distinction there? Yeah. Okay. And when you guys test this, right, don't just put in FFOF, OFOF, right, feed K dead beef kind of numbers. Also put in just like 1 plus 1, right, and test to make sure that you do in fact get 2 correctly, not 3 or something, right, or 5, which is right out. No. Monty Python. 1, 2, 5, 3 set. It's worthless. Okay. From the Holy Hand Grenade of Antioch in Holy Grail. Yeah. Okay. British humor at its finest. So, yeah. Okay. So, just wanted to point that out that you have to sometimes be careful about the flags because they could get changed on you without you realizing it. Okay. Okay, so the other thing, let's see, I wanted to start talking about was input handling, right? Which is, how did we do input handling when we were in C? If I wanted to have the user type something, what did I do? Yeah, I had to use scanf, okay, and that meant that I also had to have a formatting string, and I had to allocate where I was going to put that data in memory, and because scanf is kind of ornery, what would happen if we needed to use scanf multiple times? What function did we have to use? You guys remember the flush function, right? So we may have to worry about the flush function. Okay. All right, so let me start a new program here. Okay, and so let's go to, I call this input handling, new program, and let's just call this input.asm, whatever. Okay, so let's do data, text, global main, and then our usual suspects. Okay, so the usual stuff there. Okay, so let's suppose that, and let me change this to ARM so it highlights it nicely. Let's suppose that I want to do the following. I want to prompt to the user to type a number. I want to then say the number you typed is blah. Okay, sound good? Okay, so I actually need three things to do that. I need two strings, okay? So let's call it string one, and let's just say it's ASCII, please type a number. Okay, good. And then I could also have, say, string two, ASCIZ, and I'll put the carriage return here. Well, actually, okay, good. All right, so I've got two strings, no big deal. And then the other thing I'm going to do is, well, what kind of data do I want to have the user type in? In this example, I want to have the user type a number. What kind of number? An integer, okay? And in this case, a 32-bit integer, right? So what I'm going to do, I need to do two things. I need to have a format string to give scanf that says what kind of data it should expect, okay? And let me call this scan string. And all that's going to be is %I, right? That's what kind of data I want to hand to scanf, okay? The other thing I need to do is, like, how did I call scanf in C? I had to give it a format string, and I also had to give it what? Not a register. Someplace, where is it going to put that number? Okay, which is to say a pointer. I had to give it a memory address to say, okay, you're going to get some data, and I want you to put it over here. Okay, when you get it from scanf. Okay, so I have two options for how I could do that, and I'm going to show you guys both ways here. One is to pre-allocate some memory for it, and in the case of an integer, that's probably the better way to go because do we know in advance how big an integer is? Yeah, in terms of how many bits it takes to store it, okay? And in this case, say 32 bits, we could certainly do 64 bits also, but we know it's a 32-bit integer that we're getting, and that's it, right? So we only need to allocate 32 bits to to store it. No big deal. Okay. Where might we not know in advance how many bits or bytes we need to store an input? If the input is a string, okay? Because we don't necessarily know how many characters are going to be in that string in advance. Okay, so then we have to do something a little different. Okay, does that make sense? Yeah. Okay. So let's just allocate a number in our data section, and let's just set it to be 0 for the when the program starts, and then we'll prompt the user to write to that number, and we'll just overwrite it. Okay. Does that make sense? Sound good? Okay. So, how big did we want our data to be in this case? It was 32 bits, so that's a word. And I'll just set it to be 0x0, right? It just starts as 0. I could set this to be any number I want, but it's going to get overwritten when the user types. Okay? Good? Okay, so in my main routine, and I do not know why the syntax highlighting is all janky, what do I need to do to print the prompt to the user? Okay, I need to put what in x0? The address of this string, right? So string 1. So I need to do what? LDR x0 with the address of string 1. Yes? And then can I just printf or puts for that matter? Yeah. So I could do that, or I could do BL-printf. Why does it not matter in this case which one I do? It's just a string, and I'm not replacing any numbers in it. Okay. All right. So, oops, printf. Okay, fine. And then, so that will prompt the user. Okay, and then we need to get the input from the user. Okay. Well, if I'm going to call scanf, I have to give it two pieces of information: a format string and the place where it should put the data in memory. Okay, so where is the format string? I can't give it the format string, but I can give it the address of the format string. So what did I call my in string? Scan string. Okay, so that's the format string for scanf, but I also need to say where do I want it to put the data in memory. Okay, and where do I want to put it in memory? Wherever my num is located. Okay, does that make sense? So I'm basically giving it 2 pointers. Yes? Okay. And then what can I do? Have I set up everything for scanf? So now what? Up before that, I actually have to call scanf, don't I? Yeah? And now I can do the printing stuff. Okay. So if I want to print the number, what do I need to load into X0? The address of string 2. What do I need to load into W1? The number. Okay. So, but what am I going to have to do? String 2, LDR X2 mynum, and then I need to LDR W1 with what's in X2 indirectly. Okay. The reason is, okay, and Patrick's giving me the grimace. Okay. Why? Well, okay, because what do I have to give printf to print a number? The number needs to be where? In a register. Okay, so I don't want to give printf a pointer to the number, but rather the number itself. But where is that number itself? It's out in memory. So I need to find where it is in memory, put that pointer in X2 and then use that to load W1 with the number from memory. Okay, does that make sense? Maybe? Not at 8 in the morning? All right, and then I can print it. No? Okay, well, let's see it in action. Okay, so first off, let's make sure I didn't screw something up. And let's see, what did I call this? Input handling, and I'll go ahead and put in the debugging flags for. Okay, so it worked. That's good, right? Yes. I'm not loading the number to register to. What am I loading to register to? It's pointer, the pointer to it. And then what does this command do? Right? Remember, this is indirect memory access. This says go to register X2. Inside there, you will find a number. Take that number and go to the corresponding memory address. What you find in memory at that address, put in register W1. Right? So this is like when my dad goes to the mailboxes and he has a package and there's a key with a number on it, right? He's getting the key with the number on it and opening the corresponding mailbox, not the mailbox that, yeah? Okay, so that's what's going on, right? All right, we'll see this sort of in action here in GDB in a second. Okay, all right, so let's go to here and oops. Okay, so actually, you know what? Let me start this over because I forgot one thing. Okay, so when we start the program, this just so happens to be what's in all the registers, but I haven't loaded anything into anything yet. Okay. Um, okay, so let's step and get through the printing part. Okay, so it just did, please type a number. Okay, and what am I about to load into X0? The address in memory where I want to put, or sorry, the address in memory of the string. Okay, and then the second thing I'm about to load is X1 is going to be where in memory to put the number. Okay, but I have not yet prompted the actually taken the input from the user. Okay, so what is in register 0 and register 1? Okay, what's in register 0? It's the address of the format string. What's in register 1? The location I want to put this 32-bit chunk worth of data. Okay, so what is the pointer that I want to look at? 49B048. Okay, so that's someplace out in memory, right? All right, so let's look at what is in memory at that location. All right, what was it? 49B04. I'm going to start at 040 so that I have everything neatly organized. And let's look at it here. Okay, so what did we say it was going? 048. All right, that is right here. Okay, so these 4 bytes are 040 to 043. Okay, what are these 4 bytes? 044 to 047, and so I'm sorry, it's here. This would be 048 to 04B. Okay, in hex. Yes. Okay, why is there all zeros there? Well, what did I initialize that data variable to when I started in my data section? 0. Okay, so that's why it's all zeros right there. Okay, because I set it to be 0. If I had set it to be 17, then we would see, what would we see there if I set it to be 17? Hmm? No, I would see 1, 1 because this is in hex. Oh, okay. I didn't hear that part. Yeah, I need to check my batteries. So, okay. Yeah, but so if I had loaded any other number, right, like feed Cade or whatever, then I would see that right here because that's what I initialized this segment of memory to have. But I just chose 0 because, well, I have to do something. Okay. All right, now what's eventually going to be right here? Whatever we type. Okay. So the instruction that's about to get executed is for me to type my number, right? And then if I go to this same memory address, what should we see? Whatever number I type, okay? In hex, yes. Okay, so let's step one more, and it's going to be, it's prompting me here for the number. So this is the part where I type. So what do I want to type? Huh? Well, hey, let's do our old friend 1832. Okay. All right. Now, if I look at that same segment in memory, what do I see now? Okay. Remember 728 in hex was 1832 in decimal? Yeah. Okay. So we've seen that number before. Um, and there it is, right? So what have we done? We've told scanf what kind of data to take in and where to put it, right? Make sense? Okay. But when you say where to put it, where do you have to put it? Okay, so can a 32-bit number fit into a register? Yes. Okay, it can fit into a register, but did we put it into a register? No, we put it into someplace in memory. Okay, and to illustrate that, let's actually look at the registers. Okay, looking at the registers, do I see 728 anywhere? Well, I do happen to. It happens to be here. Okay, but did we necessarily know it was going to end up there? No. So scanf does use registers. It has to, right? Scanf is a program, and it's going to return various values. But like some of these other ones, like for example, look at what's in register 5. Does that look like, what is that? Does that mean anything to us? No. Or registers 1 and 2, do those look like, okay, 0, but what I don't know what that corresponded to. Register 0 actually is interesting, okay, because that actually allows you to do some sort of error checking on input. What kind of data did I tell scanf to expect? A 32-bit integer. What kind of data did I type? An integer, but one that fit in 32 bits, okay, because I just did 1832, okay? Do those match data types? Yes. And so scanf will actually return a 1 in register 0 if the data that the user types matches the format string given, and it will return a 0 otherwise, okay? So this gives you, at least initially, a little way of checking, did the user give garbage input? Okay. For example, what would happen if I had typed like Wabash instead of a number? Well, I'm not giving it a number, am I? Okay. And so scanf will say, hey, wait a minute, bro. You just gave me data that's not what I was expecting. Like, I'm putting a 0 in register 0. Okay. To indicate that you've just got garbage in. Okay. Okay, so the fact that X7 is 728, well, maybe that's, well, coincidence is certainly not, because, like, what are the odds of 1832 just happening to be in a register? right? Not likely. 0 or something, okay, fine, but 1832, not gonna happen, okay? So can we automatically conclude that X7 will always have the input number? Well, if it's a number that you're taking in, maybe, okay? What we would have to do, though, is like dig into the manual and see how scanf was written, okay? Does that make sense? But for damn sure, we know it's in memory, the number 1832. Okay, so if I want to print that number, then what do I need to do? If I want to print the number you typed was %I, what has to go in register X0? No, the format string. But what about the format string? I can't put the format string into X0, so what does have to go into X0? The pointer to the format string. Okay, so that's going to go in X0. What goes in W1, pray tell? The number that I want to print, right? So a %I gets replaced with a value that's in a register. Yes? Which register is the %I going to be in? Register 1. Why register 1? Because that's the next register after X0. Okay? So you're probably wondering, Julius, then why the heck did I put something in X2? Okay? See, you see in my psychic powers here, right? Okay, so so let me step and I'll show you. Okay, okay. What if I put here in W0, or sorry, X0? This is the address to the string. The number you typed was whatever. Okay, what's in X1 currently? Just happens to be 0. Okay, so if I called printf right now, what would it do? It would say the number you typed was 0. That's clearly not the number I typed, correct? Okay, so what do I need to make sure gets into register X1? The actual number 1832 needs to go there. Yes? Okay, so how do I get the number 1832 into that register? Well, where is the number 1832? Okay, it happens to be in a register X7, but let's pretend that we didn't see that. Okay, let's pretend it wasn't there. Where definitely, though, is the number 1832? It's out in memory someplace, right? Now, do we know what that memory address is? Not off the top of our heads, okay? So what I'm going to put in register 2 is the address of that data, okay? So what's in register 2? Does that number look familiar? 49B048, we used it earlier. That's the memory address where the number is located, okay? So what's the instruction I'm about to execute? It's the one there at the top, LDR W1, comma, bracket X2. Okay, so what does the bracket mean? Kind of. Okay, so what this says is look at the value in X2. That's a number. Go to memory to that address. And whatever you find there is a number, put that in W1. Okay, so this would be like, you know, I'm telling you guys, okay, go down to the basement of Sparks. I want you to open up mailbox number 2. Inside, you will find a number. Look at that number and go and open the corresponding mailbox that matches that number, right? So let's say you open up the number or mailbox number 2 and you see written on a piece of paper 49B048. Okay, what would you then do? You would go find mailbox number 49B048 and open it up. And inside, what would you find? Some number. In our case, it'd be 1832. Okay, so you see how it's sort of an indirection, sort of? Yeah. Okay, it's just mailboxes, guys. It's like, that's it. It's not that hard. Um, okay, so um, I'm about to do that instruction. So if I step and then I look at the registers, what's in register 1 now? 728 or 1832, right? Which is good. That's what's supposed to be there. Okay, and now I'm about to print it. And lo and behold, the number you typed was 1832, and our program's done. Okay? All right, so does that make sense? Ah, no, right. No, I was doing this quite nefariously. Yes? Okay, so um, let's do a second one here. Okay, what kind of data do we accept in this particular case? We accepted a number. Could we also accept a string? Sure. Okay. And we have sort of the same problem. We have to put that string someplace. Okay. Um, Now, with a string, do you necessarily know how big it's going to be coming in? Not necessarily. Okay. But what you can do is you can actually limit the number of characters by doctoring up your format string a little bit. Okay. So, for example, let me just suppose that I want to have a string of length 16. And I'm just picking 16 because it's a nice number. Okay. If I want to have a string of length 16, how many characters can I actually put in said string? Really only 15. Okay. And why? Because I need to save for the null terminator. Okay. And if I don't account for the null terminator, bad things can happen. And I'll demonstrate the bad things at some point. Okay. So I'm going to think of a string as having 16 characters, but then I'm going to make sure that I put a null terminator at that last character. Okay. All right. Is that okay? Yes or no? You're groaning. Mhm. A sigh? That was a pretty aggressive sigh. That was a Klingon sigh. Okay. All right. So let me make a new program here, and let's call that, say, input 2. Okay. And again, change it to ARM assembly. All right. So data, text, global main, main, the usual suspects, store pair. Okay, so this is all the usual. Okay, so all the usual suspects there. Okay, so in our data section, let's put in a string. Okay, so we'll get a couple strings in there. What else should we do? Well, if we're going to use scanf, we need a format string to tell scanf how much stuff to do. oops, and I forgot to put ASCIZ on these. Okay. So what data or what string are we going to pass to scanf to get a string? Well, it's going to be something like this, right? Because that tells it it's getting string data in. How many characters are we going to limit this to? Let's limit it to 15 characters. Okay. And so if I do %15s, that will do a string limited to 15 characters coming in. Now, the other thing I need to do, though, is I need to decide where am I going to put this string into memory. Okay. And if we do this sort of like we did before, what would be a good option? Well, let's pre-allocate some memory for it. Okay. So let's call this my string, and let's just make it, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. 16 characters. Okay. What's the last character? A \0? That stands for a null terminator. So this is 15 characters of 0 followed by one null terminator. Is that okay? Okay. So if I accept 15 characters from scanf, it's go are you going to live over there or go get some water or something? Yeah. Well, yeah, but I don't want you dying in the middle of class. I mean, yeah, it wouldn't look very good on my record, right? Think about the reputation I would get. Like, dude, his class is so hard that a guy actually just dropped dead in the middle of it, right?
That's what I'm saying. Take one for the team.
Well, yeah, like otherwise the class literally kills people. Oh God, could you guys imagine if Rippy were around and that happened? We would never hear the end of it. We love you, Rippy. He's probably not listening, but yeah, well. Okay, so I'm just going to pre-allocate here 16 bytes worth of data, and I'm just putting all zeros there. Now, let's be careful. When I'm typing these zeros, what really is going to appear in memory? Will it actually be zeros or something else? Okay, so if I look, will I see 16 bytes in a row of all zeros? I will not, will I, Jaden? What will I see? Well, it won't be random. It'll be whatever the ASCII code is for 0, 15 times, then followed by 00, right? The actual null terminator. Okay. So whatever 0 is in ASCII. And the only reason that it's ASCII is, well, because what kind of thing am I defining here? A string, not a number. Okay. All right. So I've pre-allocated some space in memory for this. And now the rest of the program part is going to look similar to what we did before. Okay. Um, and so let's go put this in. And I really hate that this syntax highlighting is all jacked up. Where? Oh. And it's not realizing that in a string. Okay. I'll put a dash there. How about that? Okay. Well, actually, I don't really need anything because it's okay. That's really annoying. Yeah. So, okay, I need to write whoever made that syntax highlighting package a stiff note, right? Okay. So, good. Thank you, Patrick. You have uh, you have redeemed yourself. Okay. All right. So, what do I need to do now? Well, I need to prompt the user. So, I need to do LDR x0 with the address of string 1. I need to print it, puts. Okay. So that just says, please type a string. Okay. Now I need to get the data from the user. Okay. And so what do I need to put in register 0? The address of the format string, which is instra. Okay. And what do I need to put in register x1? The place in memory I want this data to go, which is wherever my string is. Okay. Oh, yeah, I did. Thank you. X1, sorry. And then I need to branch call scanf. Okay. Good. All right, and then I want to print the answer, so I need to LDR x0 with string 2, LDR x1 with the address of my string, and then just call printf. Okay, good? Not just what now? No, because this is the thing, right? Printf expects pointers if you're printing strings, not integers, right? So in some case, it's actually easier to print a string than it is a number, right? Because I didn't have to do that indirect loading thing here, because all I have to give printf to print a string is a pointer, okay? Is that, and that's a good distinction to point out, yeah? Okay, so let's run this, make sure I didn't screw anything up, and let's assemble it, and hope I didn't screw anything up. Oop, that's good, no errors. Oops, this is input 2.0. Okay, looks good. All right, and let's also do this. Okay, I have typed way more than 15 characters. So what happens? It limits it to the first 15. Okay, now that's a good thing, okay, for reasons that'll become clear in a moment. Okay, yes? Okay, so let's run through this in GDB and look at the memory and see how this works. Oops, sorry. Okay, so let's step through like before. Well, let me just do this. Actually, you know what? Sorry. Let me start it over. Okay, so it's about to ask me for the info. Okay, so where is this stuff in memory? Okay, it just so happens to be the same number as it was last time. Okay, that's kind of coincidence. But in memory address 048 is where the string will start. Okay, so if I look at that memory address, I'll start at, again, 49B040, just so that everything's aligned. Okay, and let's look. So 040 is here, and therefore 048 starts there. So what do I see here? Yeah, okay, so I see 30, which happens to be the ASCII value for the symbol 0, okay? And I see a bunch of copies of that, and then finally, what do I see right here? 00, which is the null terminator that I put in, okay? Good? Yes? Okay, so Right now, it just has that sort of garbage data that I just sort of pre-allocated to make some space. Okay, good. If I then type, okay, that's longer than 15 characters. Okay, let's look at that same location in memory now and see what we see. Okay, so this would be starting here and ending there. All right, what do I see? What do we see? Right, so it's Wabash always fight, and it's going to get cut off at some point, right? Because how many characters does Wabash always fights? That's more than 15. Okay, so it's going to get cut off somewhere in the middle of the word fights. Okay, but so it'd be FIG. Wabash always fig. Hmm? Yeah. Okay. Um, all right. And so so what do we see? Well, those numbers are all the ASCII values, right? So what's the capital or sorry, the lowercase w? 77 A B A S H A L and then so on. W and yeah, so on. Okay, good. Okay, and by only limiting it to 15 characters, we never actually overwrite this null terminator. Okay, that's a good thing. Okay, because what can happen if you're not careful and you allow too much data to come in, right? You're telling scanf, put the data starting here. But look at what just so happens to be at memory addresses just after where our string is. Lots of stuff, okay? And if I typed a gajillion letters, is it possible that I could overwrite all of these addresses with garbage? Okay, and because those memory addresses happen to correspond to some of the other variables or strings that I'm using in my program, if I overwrite them with garbage, then bad things could happen. Yes. I could. Yeah. Yeah. And we'll demonstrate this. Let's basically take the same program, and when we had the %15s, let's get rid of the 15 and see what happens. Okay. Good. All right. And then it just prints it. And again, as we said, Wabash always fig because we limited it to 15 in this case. Okay, good. All right, so let's do the exact same thing, but remove the 15. Okay, and so now scanf will let me type as much as I want, but I've only still allocated 16 bytes for the string, but I'm going to give it way more than 16 bytes. Okay, make sense? All right, so let's reassemble it, relink it, and rerun it, and let's just go nuts. No, because if I put in some spaces, actually, scanf will stop when it hits a space unless you tell it otherwise, and I haven't told it otherwise. Okay. Huh? Well, okay. I think this is probably good enough, right? Seg fault. Okay. Now, why did that happen? Well, let's go into GDB. Well, yes. Okay, and we'll show you why the seg fault really happened. Okay, so break main, run, step. Okay, so before, let's look at, okay, so it's 49B048, that's like it was before. Oops, Let's do 040. Okay. Okay. So what we have here is okay, some of this other stuff is data that we've allocated. So for example, we had you typed the string blah or whatever. That's in memory right up there too. Okay. And if I overwrite that with garbage, okay, let's see what happens. All right, so it's about to ask me for to type something. Okay. And I'm gonna go nuts. Yeah, it's okay. Semicolons are all right. Okay, that's probably enough. Okay, now the program hasn't crashed yet. Okay, and what it's going to do here then is load x0 with the address of string 2. Now, what is the address of string 2, by the way? Well, let's find out. Okay, so those things are still okay, right? This is the address of the string, the two strings, right? So one of the strings is the thing you typed is, and then the other string that we just accepted from the user, which is all this garbage, starts there. Okay, so if I look at out into memory, starting at what is it, 49B040. Okay, what have I just done with all of this stuff? I just obliterated it with garbage ASCII values. Okay, so if I step one more time, okay, it basically just tried to print gobbledygook, okay, and it didn't actually print anything because that actually is a little surprising that it didn't print anything. That's part of it, yeah, is that I've obliterated the format string that I'm passing to scanf. So scanf probably got out to, what was the value? The format string was at 70, so that would have been here. So scanf starts looking here and probably realizes, wait a minute, I'm not seeing any format string stuff. Okay, I'm actually surprised it didn't print. Okay. Um, okay, so here's where it gets obliterated. Okay. Um, is, no, that's correct for the stack pointer. Oh, um, okay. Okay, so what the reason it's seg faulting is essentially we've overwritten data, and in particular, this stuff here basically is stuff that tells the operating system how the function terminates. And if we overwrite that with a bunch of garbage, it's not going to terminate correctly. That's why it's seg faulting. Okay. Um, now, or that's what sort of caused the seg fault. But let's remind ourselves what really is a seg fault. The seg fault occurs when you try to access memory that isn't yours. Okay. So operating systems segment memory, and they also nowadays virtualize it. Okay, so it looks like we're looking at memory address. What was it, 49B, blah blah blah. Does that mean that it's physically that spot in memory? No, not necessarily. Okay, the operating system will virtualize it so that you don't really know in memory where you are, but it does. Okay, that's sort of a modern operating system thing. But point being, operating systems from the earliest days of operating system on mainframes, right, have segmented, so they have some big pile of memory, and they're going to segment it out and allocate, okay, this program gets this chunk of memory to do its thing, and only that chunk of memory can it work with. Okay, why is that a good thing? Well, because on big mainframes, what would be the case? Like, I mean, we're talking 50 years ago computing, right? How many people would be using a mainframe simultaneously? Could be lots, right? And so there could be lots of programs running, and uh, because there's only one mainframe, right? So let's just go back to the 60s. I think I maybe mentioned this, but what was the very first computer that was ever on this campus? This campus. It was the IBM 1620. Okay. Yes, of course, right? You've all heard of that one, right? Okay. This is back when computers took up entire rooms, okay, in the 60s. Okay. So in the basement of Baxter someplace, right, in the dungeon, uh, imagine a room this size with like, it's full of a computer, a single computer that took up this room. I know this is kind of a foreign concept nowadays, right? But okay, so the computer took up the size of the room. And there's only literally one computer on campus. Okay, well, who wanted to use that computer back then? And what purposes do you think they were using it for? Huh? Data sharing, okay, and in particular, keeping track of a lot of the college data in terms of administration. How many students there are, who's registered for what, those sorts of things, okay, which back in the day would have all been on paper. Okay, and actually, this is kind of scary. You guys know how when you register for classes, you do it through self-service. You put your classes in, you hit the register now button, and then bam, you're in your classes. When I came to Wabash in the fall of 2011, do you know how you registered for classes? On paper. Okay, so this is ludicrous, right? You would go meet with your advisor, and before you had like met with your advisor would have gotten a stack of papers, one for each advisee, that had a grid, and you would write in, okay, at this time I want to take CSC-241-01 and with McKinney or whatever, right? And then I would sign it and you would sign it, and you would take it over to the registrar on your appointed day. So you know how you guys have like your day to register is November blah. Okay. The registrar's office would open at 7 in the morning, and people would camp out outside the registrar's office overnight to get in line so that they could get into the lab science class that they wanted. Okay. Now, you guys know what the weather is like. You think they should bring that back? It might build some more character. Okay. And you would go up to the registrar and you would hand them the piece of paper, and then they would proceed to type everything into the computer and register you for it. Okay. It did take forever. Okay. And it was ludicrous that we were still doing that in the 21st century, no less. Okay. So, anyway, um, back in the day, right, the, this first computer was used for basically college administration. Okay. Admissions needed to use it, the registrar needed to use it. Uh, I don't know if financial aid existed back then, but there was certainly financial data that needed to be kept track of. Okay. Um, and so if you had programs that were dealing with all of that data, they would all need memory to run. And so the memory would be segmented. Okay. So the operating system started in some sense on these old mainframes, basically because many people were using them at a time. Okay, flash forward to the late 70s, early 80s. So my Commodore 64 or my Apple II or whatever, right? Those really didn't, truly speaking, have operating systems. And part of the reason was in the early days, how many programs would be running at any given time on your Commodore? Just one. Okay, so did it matter what memory you used if all you were using was one program? No, you've got basically complete control over the entire computer. Okay, well, then what started to happen in the 80s is the operating system world from the mainframes started to get sort of moved over in some sense onto microcomputers, meaning something that fits on your desk. Okay, and that's about the time when we also started to get graphical user interfaces. So the first versions of Windows, for example, were from the 80s, right? Windows isn't the first one to do this. Like, well, let's take the Macintosh. That's maybe the one that everybody knows and loves. How many of you guys have ever seen the Super Bowl commercial for the Macintosh? Yeah, with the it's like this dystopian Orwellian nightmare. Uh, yeah, none of you have seen this commercial. Okay, of Apple Computer in the 1984 Super Bowl. Okay, look up that on YouTube. It is probably one of the best commercials ever made. Period, for anything. And it was, yeah, okay. But anyway, one of the features of the Macintosh, amongst other things, is it had a graphical user interface. And that meant that it was actually possible that multiple programs would be running simultaneously, right? The operating system or the thing that's drawing the windows, in addition to whatever programs you're using as you're doing it. And you guys know this, right? On your computers, how many times do you switch back and forth between different applications when you're working? All the damn time, right? Well, you can do that because there's an operating system that's managing all of this. And it manages it, amongst other things, by segmenting the memory so that your programs aren't fighting over the same pools of memory. Okay. And this is how you're able to switch back and forth, and it basically is seamless and magic from your perspective. Okay. Okay, so that was kind of a long-winded explanation, though, but we seg-faulted here because basically we were telling the operating system, okay, we're done, return us to your spot in the operating system code, but we gave it a garbage value, and so it's saying, nope, nope, not doing that. It's nope roping, or it's like that. You guys seen that GIF of it's like an octopus like scurrying across the bottom of the ocean, and people will like Photoshop over it. Nope, 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 nope. So it's like the nope octopus going on. You know what I'm talking about, right? No. Okay. Okay. Anyway, so the final point here, right, is if you're accepting string data or string input, be careful. Okay. And what do you do if you want to accept a ton of input that you don't necessarily know how much in advance you're going to get? We have to do something a little bit different, which is to use a thing called the heap, but we'll talk about that later. For now, let's just say if you're going to accept string input, pre-allocate space for it and limit the amount of number of characters that are going to come in. Okay, so for example, the assignment on string processing, where you'll give it a string and then it'll uppercaseify things and count how many modifications it made. Just pre-allocate, say, 16 bytes, 15 characters in a null terminator. Um, and there's nothing special about the number 16, right? Because if your program can work with 6 or 15 characters, should it be able to work with 31? Yeah, it's just more data, right? But it's the same thing, okay? So keep the strings relatively small just for demonstration's sake. And we'll talk about the stack and the heap and those sorts of things, which is other places that you can put data to stash it, I guess, next time. So, good? All right, see you guys later.